Hello everyone, this is Negar. I'm a PhD student from University of Waterloo, and today I'm going to present BERT-QPP, Contextualized Pre-trained Transformers for Query Performance Prediction. This is a work by me and my co-authors, Mariam Khodabakhsh from Shahrod University and Ebrahim Bagheri from Ryerson University. During the last few years, the information retrieval community has seen huge improvement, especially on core retrieval tasks. But regardless of all these improvements, there are still a group of difficult queries that cannot be effectively addressed. Recognizing and detecting these poor performing queries is very useful for different applications, including query routing, query reformulation, and also it can be used as a feedback to the system. Therefore, in information retrieval, we define the query performance prediction task as predicting the quality of retrieved documents in satisfying the information need behind the query. In other words, given a collection of documents, a query, a retrieval method, and the list of retrieved documents, our goal is to propose the predictor mu in order to estimate the performance of query Q with respect to a specific performance metric. And when we want to evaluate a query performance predictor, given a set of queries, we will measure the correlation between the list of predicted performance and the list of actual performance. Obviously, the higher this correlation is, it means that our predictor performed better. Query performance prediction methods use a host of potential signals that can point to the difficulty level of the queries, including the relationship between retrieved documents and the corpus, or between query and the corpus. But most of the current state-of-the-art methods relies on term statistics, and they suffers from vocabulary mismatch problem. Therefore, a couple of years ago, there were some query performance predictors that were proposed based on static neural embeddings, but they also suffers from context independency. So in this work, we are proposing BERT-QPP to address the previous drawbacks of query performance predictors. BERT-QPP directly learns the query performance through fine-tuning of BERT. We fine-tuned BERT in two widely adopted architectures, namely cross-encoder and bi-encoder architecture. Some of the advantages of BERT-QPP is that, first of all, it is context-aware, and also it does not need any additional training apart from the fine-tuning. Unlike other state-of-the-art methods, it is insensitive to hyperparameters tuning, and also it can learn performance metric of interest. So what I mean is that we can adapt this architecture to learn different metrics such as average precision or reciprocal rank, and etc. In order to train BERT-QPP in a cross-encoder architecture, we learn a continuous difficulty score based on the relationship between the input query and top K retrieved documents. Basically, we are concatenating the input query and top K retrieved documents by a special separator token. And then we have a linear layer on the first vector produced by the transformer model to produce a scalar value by sigmoid layer and one class binary cross entropy loss. You can find more details about our loss function and BERT-QPP cross-encoder architecture in our paper. And we should note that in these architectures, we are specifically learning desired ranking metrics such as average precision or reciprocal rank. And in BERT-QPP bi-encoder architecture, we have the query and set of retrieved documents, and we feed them into a Siamese network architecture, which consists of two parallel towers. We embed the query and topkey retrieve documents separately, and then we try to learn the association between the query and top retrieve documents through some similarity metric. Basically, this similarity metric represents the performance of the query. Again, you can find details of loss function for this architecture in our paper. Let's compare the BERT-QPP bioencoder versus BERT-QPP cross-encoder. Obviously, in BERT-QPP cross-encoder, we are having the query and documents in the same network. Therefore, there are a higher number of interactions. And then this higher number of interactions leads to capturing deeper association between the query and document space. But in BERT-QPP, we can embed the documents offline. Therefore, it will help to have lower inference time, and it's more efficient and faster compared to BERT-QPP cross-encoder. Let's go to our experiment section. We run an experiment on MS Markov passage collection, which includes 8.8 million passages, more than 500,000 query and relevant documents for the training set, and also we test our proposed approach on 3 different query sets. One is the almost 7,000 development queries in MS Markov collection, and 2 of the track deep learning track from 2019 and 2020. These the track collection versus MS Markov queries are different in terms of how they have been judged. The former has sparse labels, and the latter has been truly judged in 0 to 4 level judgments. When we compare these 2 different sets of query, we can study the robustness of our metric, and we can show that if our proposed QPP methods are robust to different judging criteria or not. And we have retrieved 1,000 documents per query for BM25, and we evaluated the queries with official MS Markov leaderboard metric, which is MRR at 10. We considered many of the state-of-the-art query performance predictions as a baseline, some of which are unsupervised metrics and mostly based on term frequency and corpus statistics. And also we considered some supervised metrics such as neural QPP, which uses unsupervised query performance predictors as a for a weak supervision learning. And also we considered NQA QPP, which is the most similar method to our work, which is also based on contextualized pre-trained embedding. But the thing is, we distinguish our work from this work because they have 3 key components in their work, which is the retrieval score component, BERT representation of the query, and BERT representation of the query and retrieved documents. They use all these 3 components as an input of a second feed-forward neural network. And the second network is trained to predict the performance of query. Thus, their method has several neural networks, and it's more expensive than BERT-QPP. Let's look at some of our results and findings. In this table, we report the performance of our proposed methods as well as state-of-the-art baselines in terms of Pearson row, Kendall tau, and Spearman row correlation on 3 different query sets: MS Markov, Track Deal 2019, and Track Deep Learning Track of 2020. As you can see, all the contextualized based QPP methods, including NQA QPP and 2 variations of BERT-QPP, show highest correlation across all the query sets. Among the contextualized pre-trained models, BERT-QPP cross shows consistently better performance over all the baselines. And unlike most of the baselines, both BERT-QPPs shows stable performance on all 3 query sets, because some of the baselines performs very well on some query sets, but performs poorly on other query sets. And between BERT-QPP bioencoder and BERT-QPP cross-encoder, BERT-QPP cross-encoder architecture shows better results compared to the bioencoder one. Since query performance prediction should be applied at the inference time, the runtime is super critical. Therefore, we compare the inference time of neural-based QPP baselines when running on an RTX 3090 GPU. As you can see in this table, we report the inference time of NQA QPP, neural QPP, and two of our methods, which is BERT-QPP cross and BERT-QPP bi, in terms of milliseconds. Bioencoder, BERT-QPP bioencoder shows significantly lower inference time, almost 4 times smaller than the cross-encoder one, which was expected. And if we want to compare this inference time compared to a retrieval inference time for BM25, which is 55 milliseconds, this time is very reasonable, and it makes the BERT-QPP methods very tolerable, and it makes it practical for real-world problems. And if we want to compare our proposed approach to the state-of-the-art neural-based QPP models, we can say that our slower variation, which is BERT-QPP cross, is at least 8 times faster than the fastest neural baselines, which is neural QPP. To conclude this work, we can say that we propose the contextualized pre-trained transformer-based QPP method that it learns to estimate the performance of retrieved list of documents for a given query. And we propose 2 variations, namely BERT-QPP cross and BERT-QPP bioencoder with different architectures. And we conclude that while the cross-encoder ones enjoys a consistently stronger performance, the other one is more efficient. And we showed that both BERT-QPP cross and bioencoder are substantially faster than existing neural QPP methods. Thank you for listening. I would be happy to answer your questions about this work. You can ping me at my email or on Twitter. Thank you.